Hello everyone, I hope you'll be fine. So I'm back again with the next topic on O-level physics, and this is about the waves. So since my previous videos, the syllabus has been changed now, and now I'm gonna start off with this topic like waves, and then we'll have like some more topics. So from now onwards, I'm gonna proceed with the new specifications as it has been given in the GCSE Cambridge curriculum. So in this topic, in this chapter of waves, we have four subtopics. Number one is about the general properties of the waves. So in this topic, first of all, we'll discuss about the general properties of waves. So in this topic, we'll discuss just about the general properties of the waves, and then comes the light, and then we'll discuss about the electromagnetic spectrum, and after that, in the end, we will discuss about the sound waves. So in waves, first of all, we have to discuss like what are the waves and why are they used. So basically, the waves are used to transfer the energy from one point to another without transferring the matter. All right, so I'm just gonna write it over here. Waves are used to transfer energy from one point to another without transferring the matter. So these are the waves. For example, let's suppose there's a string that is attached to a wall like that. This is the wall, and this is the string. We move the spring up and down from this side. So as the spring moves up and down, it transfers the energy from this point over that point. All right, so basically, as we move the spring up and down, the energy is being transferred from this point to that point in the form of wave. So that's how we can explain how the energy is transferred from one point to another point. All right, now let's take another example. So for example, we have water surface over here. This is water, right? And someone throws a stone into the water. All right, so when a stone is thrown into the water, circular waves will be formed over here like that. So these waves, they will spread out, and that's how the energy is transferred from this point in the outward direction. So after this introduction, let's discuss some of the features of a wave. So let me just erase it all, and we'll discuss some of the features of the waves. Features of waves. So in these features, we have to discuss wavefront. We have to discuss the wavelength. Then comes frequency. Crest, trough, amplitude, and in the end we have to check the wave speed. So in order to discuss these features one by one, let me just start off with the wavefront. So for the wavefront, for example, this is a wave. If we see this wave from top, it will look like this. So this is the top view, and this is the side view of the wave. All right, now observe it carefully. This point over here is being represented by this line. This point over here is being represented by this line, and this point over here is being represented by this line. So these are called the wave fronts, right? So in other words, the tops or the peaks of the wave, they are the wave fronts, right? So whenever we see the wave from the top, these lines will represent the peaks, and the region in between these, exactly in between these lines, will represent these lower peaks. We'll discuss that top peaks and lower peaks in the next features. Okay, so the next feature that we have to discuss is the wavelength. So wavelength. So for example, I have drawn a wave over here. So the length from this point all the way to this point, or the length from this point or this point, or the length from this point of the wave to this point. These are all the same lengths and they are called the wavelengths. But before that, I want to explain you about the crest and trough. This positive peak that you are seeing, this is the crest. This is the crest. And this bottom peak that you are seeing, these are the troughs. So the positive peak is the crest and the negative or the bottom peak is the trough. So the distance between two consecutive crests or the distance between the two consecutive troughs is called the wavelength, or the distance that a wave complete in one cycle is the wavelength. So the cycle of the wave starts from here. That's the quarter cycle. Over here, half cycle, 3/4 of cycle, and a complete cycle. So that's why the distance from the beginning to the end of the cycle is called the wavelength. All right, so we were discussing about the wavelength. So let me just write wavelength over here. So crest, as I told you, is the positive peak, trough is the negative peak, and wavelength is basically, let me just write down the definition over here, the distance between two consecutive crests or two consecutive troughs. That distance is called the wavelength. All right, so we have discussed three more features of the wave: wavelength, crest, and trough. So the next feature of the wave that we have to discuss is the, let me undo it. So So the next feature that we have to discuss is the amplitude. So let's suppose this is the middle of the wave. Now amplitude is basically the distance. Okay, basically first of all we have to discuss the position. So this position of the wave is the mean position, and this position over here, that's the extreme position. Similarly, this is the so this is the positive extreme, and that's the negative extreme. Positive extreme, negative extreme. Now amplitude is the distance between the positive extreme and the negative extreme. So we can say that the distance from the mean position to any of the extreme position is the amplitude. So these blue lines are representing the amplitude. So that's the amplitude of the wave. By definition, we can say that the distance between the mean position and the extreme position is the amplitude. Right? So this is the definition for the amplitude. So this is another feature of the wave. So after amplitude, we have to discuss the wave speed and the frequency. So let's move on towards the frequency. Let me just erase it down. So I'll explain you frequency by its definition. Frequency is basically the number of cycles of a wave traveling through a point in 1 second. In 1 second. For example, we have a wave. This is the wave. These are the cycles of the wave. One cycle starts from here, ends here. Starts from here, ends here. Second cycle, third cycle, fourth cycle, fifth cycle, sixth cycle. So let's suppose these 6 cycles are passing through a point. Let's suppose the point is over here, point A. So let's suppose these 6 cycles are passing through this point A in 1 second. So we can say the frequency of this wave is 6 Hertz. Why 6 Hertz? Because there are 6 cycles passing through A in 1 second. So that's why the frequency is 6 Hertz. Hertz is the unit of frequency. Let me just write it down over here. We represent the frequency with small f, and the unit is Hertz. And we represent the unit with the symbol Hz. So that's how you'll explain the frequency. Now the next thing that we have to discuss is the time period. So let me just erase it. Time period. So time period is basically opposite of the frequency. We represent time period with capital T, and by definition, time period is the time it takes for a wave to complete one cycle. For example, we have a wave. This is the wave. This wave starts from this point. It covers quarter cycle, half cycle, 3/4 of cycle, and complete cycle. One cycle has been completed at this point. So the time it has taken to complete this cycle, this first cycle, is the time period. For example, this wave took 6 seconds to complete these 3 cycles. So for one cycle it will be 2 seconds. Or in simple words, you can just say the time it takes for a wave to complete one cycle is the time period of the wave. So the time from here to here is the time period. We represent capital time with capital T, and let's discuss the relationship between the time period and the frequency. As I told you that time period is opposite of the frequency, so let's discuss its relation. So frequency is equal to 1 over time period, and symbolically we can write F equals to 1 over T. And by the way, the unit of the time period is seconds. We measure the time period in seconds. So if the time period is given in milliseconds or microseconds or hours or minutes, we have to convert that into seconds. So that's the formula that relates the frequency and the time period. F equals to 1 over T. So this is the relationship between frequency and time period. Now after that, we have to discuss about the wave speed. Wave speed is simply the speed of the wave with which it travels. So wave speed is related with frequency and the wavelength. So we can write it as speed of a wave is equal to frequency multiplied by the wavelength. So V is equal to F lambda. So lambda is basically the symbol to represent the wavelength, and the unit of wavelength is meters, and V represents the speed. So V is equal to F lambda. So this is the relationship of the wave speed with frequency and the wavelength. So these are some of the features of the waves that we needed to discuss. And now we have to discuss about the transverse waves and the longitudinal waves. Like, there are two types of waves, the transverse waves and the longitudinal waves. So let's jump into that. Alright, so now we have to discuss the two types of waves, the transverse waves and the longitudinal waves. So let's write down the definition first, and then I'll explain you like what are the transverse waves and what are the longitudinal waves. So transverse waves are the waves whose direction of vibration is perpendicular to the direction of the wave. I repeat, the waves whose direction of vibration is perpendicular to the direction of the wave. For example, our wave is vibrating up and down, but the direction of the wave is to the right. So you see, the wave is vibrating in the vertical direction, and the direction of the wave, the vibration is in vertical direction, but the direction of the wave is in horizontal direction. So it is moving in, the wave itself is moving in the horizontal direction, but the vibration is up and down. So such waves are the transverse waves, so where the vibration is perpendicular to the direction of the wave. Now, for example, the light waves, all type of light waves are the transverse waves. Second, the water waves, they're also the transverse waves. And the waves in a string, they're also the transverse waves, right? Moreover, we have the seismic waves. Seismic waves are the waves that are produced by the earthquake. So there are two types of seismic waves, S waves and P waves. Among those two types of seismic waves, the S waves belong to the transverse waves, and the P waves, they belong to the longitudinal waves. I'll explain you. So these are the transverse waves. So the most important thing that you have to remember in the transverse waves is this phenomena: the direction of the vibration and the direction of the wave. So the wave is moving in the horizontal direction and the vibration is up and down. So they are perpendicular to each other, which means it's a transverse wave. Now let's discuss about the longitudinal wave. So by definition, the waves whose direction is parallel to the direction of vibration. So these type of waves are the longitudinal waves. For example, the wave is vibrating in the horizontal direction. So this is the direction of vibration, and the wave is also moving in the horizontal direction. So this is the movement of wave. So you see, this movement is in horizontal direction and that movement is also in the horizontal direction. So these two movements are parallel to each other. So such phenomena happens in the longitudinal waves. Now the type of longitudinal waves are the sound waves. All type of sound waves are the longitudinal waves. And seismic waves. So from the seismic waves, the P type of waves are the longitudinal waves, right? So these are the differences between the transverse waves and the longitudinal waves, right? P means, and the P waves means like the primary wave, and S wave means the secondary waves. All right, so this is it for the types of waves. All right, so after this we'll discuss some of the properties of the waves. So in the properties of the waves, we have to discuss the behaviors of the waves. So properties of waves. Number one, waves can show reflection. Number two, waves can show refraction. Number three, waves can show diffraction as well. So these are the three main properties of the waves. So let's see what is reflection. Reflection means, for example, this is a plane surface. A wave hits this surface and bounces back. So this is the reflection. Okay. For example, let's discuss the water waves. So I'm going to draw the wave fronts for the water waves. So these are the wave fronts of the water waves. So they are hitting this water surface and hitting this surface. This is the plane surface, and bouncing back. Look at this. So this plane surface has just changed the direction of the water wave. So this is the reflection. Now you can observe one thing. The distance between these wavefronts has not changed. The distance between these wavefronts is constant. So this is what happens in the reflection, because if the distance between these wavefronts change, it means its speed has changed. The speed of the wave has changed. But over here, since it's unchanged, so which means the speed of the wave will not change under reflection. Now the next phenomena that we have to discuss is refraction. So in refraction, what happens is a wave, let me use black color, a wave enters from one medium to another. This is basically the refraction. So when a wave changes its medium, let's suppose a wave enters from air, a light wave enters from air into the glass, air into the water, air into the diamond, so its behavior will change. By behavior, I mean its speed will change, its frequency will change. Frequency will, when I said, the wavelength will change. So when a wave enters from one medium to another, that's called refraction. So we have a medium over here. So let's suppose this is a glass block, and over here we have air. A light ray enters from air into the glass. So this is the surface, this is the boundary of the glass. Now instead of moving straight, it will not stay straight. It will bend a little bit. It will show some bend like that. So it was supposed to move straight, but it has shown some bend. So this is basically refraction. So when a light wave or any other wave enters from one medium to another, its direction changes. Its speed changes depending on the type of material in which it is entering. We'll discuss it later on in the topic of light. But for now, just to get an idea, refraction is basically when a wave enters from one medium to another. That's the refraction. Now the next thing that we have to discuss is diffraction. Diffraction. So diffraction is basically, it is the spread of a wave when it escapes from a narrow opening. That's the diffraction. All right. So the spread of a wave when it escapes from a narrow opening is the diffraction. For example, there's a light wave, and this is a small narrow opening right over here. That's a small narrow opening. A light ray is coming over here. For example, there's a light ray, it's coming over here. Right over here. So there's a light ray coming over here. So after passing through this narrow opening, this light ray will spread. It will spread like this. So the spread of the wave is called the diffraction. Obviously this is a bit inaccurate figure. Let me just correct it. So it will spread from this narrow hole like that in all the directions. So this spread is represented by diffraction. There you go. So in this way, the waves diffract. Now we'll discuss how this narrow hole affects the diffraction of the wave. So if this narrow hole, if this opening right over here, if the size of this opening is equal to the wavelength of this wave, then the spread will be maximum. So I will write it over here. When the narrow opening is equal to the size of the wavelength, in that case the spread will be maximum, or we can say that diffraction will be maximum. For example, the length of this narrow opening is L. Okay, so if the length L is equal to the wavelength lambda, in that case the diffraction will be maximum. All right, so that's how you can tell about the diffraction of a light, of any wave basically. Okay, so now we'll discuss some more properties of the wave by drawing a ripple tank. So ripple tank, so it's a tank with a top where there's a transparent sheet at the bottom, and there's a light lamp at the top. There's light coming from here, and there's a white sheet at the bottom. That's the white sheet at the bottom, and we have the water waves over here. I'm just drawing the wave fronts of the water waves. So these are the wave fronts of the water waves. Now these wave fronts, let me just redraw the wave over here. Let's suppose this is the wave. So these lines over here, they're representing the crests of the wave. Okay, and the region in the middle of these lines, that region is the trough of the wave. All right, now when the light turns on, it falls on these water waves, and wherever there are wave fronts, we will see some dark regions over there. So we will see some shaded regions. Let me just draw with some right over here. We'll see some dark regions. You see over here. So these dark regions are being shown on this paper sheet, on this sheet, white sheet. So these dark regions are representing the crests, and the region in the middle, this region is being represented by the troughs. Now if you want to calculate, if you want to measure the wavelength, so for that purpose we just have to measure the distance between any two consecutive dark regions. So these are the wavelengths. So that's how we know the wavelength of the water waves by using a ripple tank. Now let's do some alterations in this ripple tank. Over here till this region, the length of the you can say the depth of the ripple tank is more, and over here the depth of the ripple tank has become less. Okay, so we'll see what happens to the wavefront when the depth of the ripple tank changes. Remember, depth is more over here and depth is less over here. So now I'm going to make some changes in the wavefronts and you'll observe those changes. So I'll also remove these lines as well. All right, so when the depth increases, the water waves will, the wavefronts will come close to each other like that. These are the wavefronts. All right, what does it say? We know that V is equal to F lambda. So you see over here the wavelength is more and here the wavelength is less. So as the wavelength decreases, the speed of the waves will decrease. So we can say that as the depth of the ripple tank decreases, the speed of the wave will also decrease. Why? Because the wavefronts become close to each other and the wavelength decreases. As the wavelength decreases, so that the speed of the wave will also decrease in this region. So this is the region of less depth and this is the region of more depth. Got it? Now same happens with the results in the on the sheet at the bottom. So we can say that it will look like so just a second. Yeah, so these are the dark lines that we'll observe on the white sheet like that. All right, so the distance between these dark lines has decreased, which means the speed of the wave has decreased. So as a conclusion, we can say that, I'll just write down my conclusion over here. Let me just find some space over here. The speed of the waves will decrease when the depth of the water decreases in the ripple tank. And why does it happen? It happens due to decrease in the wavelength. So that's the whole story of the ripple tank. I hope you got it. So this is it for the first section of the waves, and now the next section will discuss about the light, like the light waves. So these are some of the general properties of the waves that we needed to discuss, and according to your new syllabus, and when you see your curriculum, it's the topic 3.1. Now the next topic is 3.2, that is of light, and we'll discuss that in the next video. Thank you.